group satisfying a similar property. All right? Okay. Now for the real punchline. Let's give you a sense of how powerful this theorem is with an example question. Take the non-zero complex numbers, and the binary operator is multiply. So this is a group called G, or G1, like. And take another group of the reals, non-zero, the non-zero reals. So R star. Remember, star just means kick out the zero. So R star, and again the binary operator is multiply, but this time multiply by multiplication of reals, and this multiplication sign here means, as binary operator, means multiplication of non-zero complex numbers. Okay, so call this group G2. Okay. Question: are these two groups? Now they're groups. Right? We know that the C star with this binary operation is a group. Right? We proved that way back. And similarly, R star with a similar binary operator, also a group. So we have these two groups. Question: are these two groups isomorphic? Okay. So to find a counterexample, I mean, to prove that they are not isomorphic, we only have to find one counterexample. Right? That's the great beauty of proving, or rather disproving, a hypothesis, is you only have to find one counterexample. So let's try to find one, and we will then show that these two groups, the C star, the multiplication of complex numbers, and this one, R star, multiplication of reals, non-zero. So if we can just find one counterexample that these two are not, where the number of solutions. Well, here's the problem. Let's just choose an n. So let's choose n as 4. So n is 4, let's say. And the unit for this group is 1. And similarly for this one. So we'll call that x. So x to the 4th is 1. Right? Now I put z here because it's a complex number. Right? Now, question: how many solutions does this have in this group? How many z's are there that satisfy this property? So how many of these for this group? And I put a z here because it's a complex number. Well, if you know complex number theory, you will recognize this as the z here is the 4th root of 1. Okay? And if you know a bit of theory, you know that z. So that means z can be 1, minus 1, I, or minus I. Right? That they are the four fourth roots of 1. And the number you have, the size of t, if you like, is 4. Now, and they all, all these z's, 4 of them, they belong to C star. They're non-zero, they're complex numbers. All 4 of them belong to this group. Now, what about the reals? So x now is a real. How many solutions does it have that for x to the 4th is 1? Well, it only has 2, right? So x can be 1 or minus 1, and that's it, right? You can't have complex solutions here because x is real, right? You're restricted to the reals. So it only has 2 solutions, whereas this one has 4. And therefore you've got this situation. You have a difference in the number of solutions, therefore not the same. Okay? So you have this, not the same. And by this logic, if isomorphic then the same, but not the same, therefore not isomorphic. In other words, this group and this group are not isomorphic. Wow. So you've proved that C star and R star, you can't map them isomorphically. Can't do it. Right? All because of this very powerful theorem. So impressive. Okay, I'll stop there, and then next session, we'll start on some theory on finite abelian groups. Now that's quite a large topic, and when I was reading through it first time, I was wondering, well, why did Barnard put that in the chapter on isomorphisms? And I suspect, I'm not certain, but I suspect it's very beautiful theory, and it's leading up to a major theorem in group theory, which is the classification of finite abelian groups. Now that's sort of borderline between, say, senior level and first year masters. So he doesn't, in later session I'll do other theorems where Barnard does not give proofs, so it's more in M1 level. So when I come, oh, by the way, if I can find it. So if you're really interested in group theory, a serious candidate when I come to give lectures on M1, that's first year master's level lectures, or lecture sets, probably, but I'm not quite certain yet, but probably the textbook I will use for the M1 course is by Humphreys. So it's John F. Humphreys. The title is A Course in Group Theory, and it's by Oxford University Press as the publisher, so A Course in Group Theory. And in this textbook, which is sort of M1 level, about half of it, I guess, he talks about the classification of finite abelian groups. And so maybe to finish up, maybe quickly talk about what classification means, because it's a feature, one of the highlights, if you like, of group theory, finite group theory. To classify, what does that mean in the context of pure mathematics? It means to make a list of all possible types of whatever it is that you're talking about, and I'm being a bit vague here, but deliberately. So you make a list of all the types you think exist of a certain kind, and then you prove that that list is complete. That's all the possible cases that there are. Right? There can't be a further case, because you proved there cannot be another case other than the ones in the list. Right? That's a classification theorem. And I think pretty well it's unarguable. The most famous classification theorem in pretty well all of mathematics is the classification of the finite simple groups. Now I keep mentioning this because I'm rather obsessed by it. This enterprise was enormous. It was finished, well, in a sense it's still not finished, but effectively finished early 80s, so about 30 years ago. And it was, it involved about 15,000 pages of academic journals, and about 400 mathematicians collaborated on this enormous proof, proving that the list that we're talking about, of a list of all the so-called simple groups. Now, a simple group is not simple in the sense of easy to understand. In fact, the full understanding of all the simple groups is still something that evades us. The research mathematicians are still working hard on the simple groups. But simple in the sense that you cannot break down that group into smaller parts of a certain kind, and again, being vague. Now, the largest of those so-called simple groups is the monster. The monster, its order, is of the order of about 10 to power 53. That is 100,000 trillion, 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 trillion elements. It is enormous. Okay? Now what's so fascinating about the monster group in the set of all the simple groups is that it has intimate links with string theory and hence physics, right? And it's that's what fascinates me. So I will go as high as I can in teaching the simple groups, because I'm sensing that physics and the simple groups will connect much more intimately than they have already. But there's already quite a strong connection. And I think I've mentioned this once before, but there's a guy, an English-American guy called Borcherds, B-O-R-C-H-E-R-D-S, I think, Borcherds. He's now at Berkeley, I think. Now he got the Fields Medal, it's sort of like the Nobel Prize, in mathematics for showing that there exists a 26-dimensional string theory that closely involves the monster. Right? There's a particular kind of algebra that he created that connects intimately with the monster. And a lot of mathematicians, research mathematicians, still feel there's a lot yet to still be mined, to be extracted, to be discovered about the properties of the monster and similar simple groups, not quite as big but still huge. And the mathematical physicists sense also that a future wedding is to be held. So one of the things I really like to do, if in the future I can get quite a following, is to make an appeal to some of you, is to get curious about these simple groups. And if you're a math physicist or a mathicist, you just do math physics, maybe you might become inspired to learn a lot about these simple groups and hopefully use them to create future physics, future theoretical physics. That's one of my dreams, either as a teacher to inspire others, or perhaps maybe I'll just myself hit on something. All right, well, I'll stop there, and the next section we'll start on some theory of finite abelian groups and do a few theorems there. Although we won't go too far because it's getting into first year master's level, right? And this is supposed to be a junior senior course, but it'll give an introduction at least, so to the next section.